Welcome to the impossible frontier of gas chromatography. In our previous units, we learned how to make molecules fly through derivatization. We mastered the oven and the column. But let's be honest, what if your sample is a chunk of a car tire? A high-performance polymer? Or a single flake of paint from a crime scene? You can't dissolve them, you can't melt them, and you certainly can't inject them into a standard GC. It is the ultimate no-entry sign for most researchers. But not for you. Today we learn how to break the rules of matter. Welcome to Pyrolysis GC. Imagine you are staring at a sample that refuses to cooperate. It's solid, it's stubborn, and it's cross-linked. A standard GC user would give up. But a specialist sees this solid not as a wall, but as a vault full of information. We are going to use the sledgehammer of precision to crack that vault open. We aren't just heating things up. We are performing a strategic deconstruction to turn indestructible solids into a detectable gas phase fingerprint. If you can't go around the wall, you go through it. The roadmap to the inferno. Today we navigate 4 strategic sectors. Sector A, the physics of cracking, why burning is your enemy. Sector B, the hardware, choosing between furnace and filament pyrolyzers. Sector C, reading the pyrogram, using the Lego castle analogy to reconstruct the truth. And finally, Sector D, real-world forensics, from microplastics to hit-and-run investigations. This is the ultimate toolkit for handling the uninjectable. Most people hear heat to 600 degrees and think of fire. But fire is the death of data. In a lab, burning requires oxygen and turns your sample into ash and CO2. Pyrolysis is different. It is thermal degradation in an inert atmosphere, usually helium. Because there is no oxygen, the molecules don't burn. They snap. This is the difference between a mess of soot and a beautiful, high-resolution chromatogram. We want chemical fragments, not smoke. We want to see the architecture, not the debris. When you apply enough thermal energy, the covalent bonds in a polymer chain vibrate so violently that they break. This process is predictable and reproducible. Every polymer has a specific fracture pattern. By controlling the heat, we force the solid to exhale its chemical identity. If you control the physics, the chemistry will follow. As a specialist, you have 2 primary weapons. The furnace pyrolyzer is incredibly stable and easy to automate. You simply drop the sample cup in. But the filament pyrolyzer uses a platinum wire that heats up in milliseconds for those who need surgical timing. An operator hits the temperature button and hopes for the best. A specialist calculates the rise time to ensure the molecules snap before they have time to undergo messy side reactions. It's about being faster than the chemistry. If your rise time is too slow, your sample melts and degrades into a broad, useless blob before it even enters the column. We want flash pyrolysis, an instant jump to 600 degrees. This speed is how we achieve the sharp, high-definition fingerprints we need for mass spec. We want the molecules to shatter before they can think. This chart represents the efficiency gain when you master the thermal rise time. Low TRT equals high discovery. Think of a polymer like a massive Lego castle. If you smash it correctly, you'll find predictable pieces. Looking at this polystyrene pyrogram, those repeating peaks are the molecular signature. By looking at the fragments, we can tell exactly how the original solid was built. A technician sees a mess of peaks. A specialist reads a structural story. This is how we identify a mystery plastic in under 30 minutes without using a single drop of solvent. We find the bricks to understand the castle. Why go through this trouble? Because PYGC per megasiemens is the gold standard for microplastics. Unlike microscopy, which only looks at shape, we measure the actual polymer mass. We can identify a hit-and-run vehicle from a single paint chip the size of a salt grain. PYGC provides audit-proof evidence from samples other techniques can't touch. It is the specialist's secret in high-stakes litigation and environmental auditing. From one flake of paint, we can trace a manufacturer's resins. A pro move is reactive pyrolysis, adding TMAH directly to the solid to perform surgery in the heat. We also use EGA, a slow temperature ramp that creates a thermogram to find exact transition points. This is strategic deconstruction at its highest level. You aren't just heating things up. You are mapping the physical properties of the matter. You are the architect of the inferno, deciding exactly when and how the molecules should exhale their truth. Summary: the mastery of the solid. We've moved from indestructible solids to gas phase fingerprints. You now understand the difference between cracking and burning, the importance of rise time, and how to read the Lego pieces of a pyrogram. Don't be limited by liquids. You now have the tools to analyze the entire material world. If nature didn't give you a solution, the inferno will. Respect the vapor pressure, and the solid will reward you with its story. You've mastered the one-dimensional race. But what if your sample has 1,000 components all crossing the finish line at the same time? A single column won't be enough. Join me in our next unit, Module 4-4, Dimensional Power, where we leverage GC to resolve thousands of compounds. We're going to add a second dimension to your mastery. I'll see you at the next starting line. Are we ready to add another axis to the race? I'll see you in the next module.